Okay. Okay. Can you see my slides?
Yes.
Okay. Let me try to hide anything else from Zoom. Okay. Yeah, I'm going to talk about scheduling on heterogeneous resources, how we integrate these resources into the CMS workload management and submission infrastructure. So, well, a bit of motivation, although perhaps it's not necessarily the most important part at this point of the workshop and the session. Yes, we want to use HPCs because these are going to be a non-negligible, in fact, a very sizable portion of the computing resources that we will have available in the future, even not in the long-term future, but closer than that. And in particular, we know that a big fraction of this computing power will not be available in the form of CPUs. So I'm just here providing the example of the BSC, the case of the Spanish Supercomputing Center, in which the next machine, Mare Nostrum 5, scheduled in a year from now, it's going to be a pre-exascale machine, and it's explicitly stated that it will be an heterogeneous supercomputer. So we need to be able to take profit from these resources. For CMS, CMS is currently investigating how to run on heterogeneous CPUs and GPUs. The main focus for run 3 is in the HLT farm. In a bit of more longer term, it's also on the grid. But again, we are moving towards that goal as of now. So we just discuss about the code and the framework. So I will not go into this. I will just mention that regarding offline processing, even though we have a limited number of available GPUs already for CMS in our grid infrastructure, in particular in a few sites in the US, the code which has been rewritten already is still not used, or it takes an insignificant let's say fraction of the computing time. So this is still not relevant in offline computing. Well, considering the use of GPUs, of course, a model for the work management, well, for the scheduling of the jobs and the acquisition and the integration of the resources, we need to consider what is the model on how we are going to be allocating these resources, how they are installed, basically, and also then what is our plan on how to schedule on these resources. So, for example, yes, are we going to be dealing with dedicated GPU resources, or as part of a broader mix and heterogeneous installation, like, for example, this HPC in Barcelona, which I just mentioned? And then how do we want to schedule work? Will the workflows be specifically targeting GPUs, or do we want in general to have our jobs be able to run anywhere and use the resources as they appear to them? So we just discussed that. In fact, it seems to be the second way that we want to do in CMS. So we want to use GPUs in a transparent way when they are available. This, however, this second mode of operations already raises concerns from operations point of view. In particular, we are already considering only CPUs. There is already a sufficient CPU power spread, let's say, between all the different models that we have in our global pool. This causes a spread in the runtime of the jobs as we distribute these jobs in the grid. So if we add more resources and we are adding, in particular, GPUs and different ways of running, the concern is that it's going to be very difficult, impossible to determine the runtime of the jobs. And this is going to be causing some trouble in the scheduling of these jobs. So, like I said, already today, there is a certain level of spread. Perhaps this will be increasing when adding GPUs on top of it. So basically, considering how we will find the resources which will be available to us, and also how we want to use them, Then we need development in both stages, let's say in CMS, which we call in our jargon, it's the workload management layer and the submission infrastructure layer, which I will now explain. This is very briefly how we run jobs in CMS. So we start with the request on top, which comes from the physics groups, and this provides the job configuration data set, the version of the software, conditions to use, etc. This Monte Carlo management uses information to create a workflow, which is then passed on to the workload management. The global work queue produces the workflow and partitions the workflow into chunks. These are the work queue elements. And then we have the WM agents, which pull chunks of work and materialize them into jobs in the Condor sense, okay, populating the queues in the Condor submit nodes, the schedules. At this point, we are entering now in the domain of the submission infrastructure, which basically means the Condor pool that we have spread all over the grid. So these jobs are now in the schedules, and they have requirements such as the site where they want to run, memory, CPUs, storage needs, etc. These jobs generate pressure on the CMS Glidein WMS frontend and the pilot factories. So pilots are submitted to the resources where they request resources by means of a CE, for example. They get the resources, and these resources join the CMS global pool. So once a slot is running, of course, then we have the matchmaking in Condor, where the collector and the negotiator take care of the matchmaking, and finally the jobs get matched to the available slot. Okay, so this is a typical let's say late binding pilot-based model, which is the core of the way that CMS works. Okay, so having had this distinction between these two stages, workload management and submission infrastructure, let me explain a bit adaptations in each of the two needed for usage of GPUs. So in the workload management side of it, so basically the main point is to have these jobs properly identified. So which jobs are able and are requesting to take advantage of GPU resources. And specifically, we need this type of information to be available. So is the use of the GPU optional, or is it required? Is the decision to use it or not predefined, or to be defined at runtime, for example, depending on the availability of the type of GPU or other variables? If it's predefined, and we know that this is a particular configuration in which the jobs will run, so perhaps we will need to flag and validate each of the requests individually. I mean, in a different configuration that they're running. And finally, an important thing for us is that we are trying to group the several steps in our simulation. So generation, simulation, DG, and RICO. We are trying to put all four of them together into a single task, which can run, let's say, from start to the end. Okay, because this minimizes the number of intermediate states, intermediate files, etc., that need to be tracked and keep in the bookkeeping. And also it alleviates as well the management of the whole change of workflows. Okay, so let's assume, and we are going in the direction of joining all these steps into a single chain. However, so how do we integrate that with the use of GPUs? So do we need to define a number of, or a type of GPU which can be used in each of the execution steps? So as we are trying to run this as a single entity, this information is, let's say, is needed to beforehand, so that we can be scheduling these workloads properly. So the WM core and request managers for CMS, they need to support the new request parameters. So type of GPU, so use or not of GPU, etc. And these parameters need to be propagated from the request onto the job class set. Once the workflow has been partitioned into jobs in the Condor sense, this information needs to be propagated to the class set so that we can go on to the next stage, the Condor stage. A very simple view on CMS submission infrastructure. This was shown in Adelaide. I will just concentrate, and I want you to look just at the right-hand side on the blue text, let's say. I'm just showing this because we have several ways of incorporating HPCs into CMS pool, or into the CMS resource pool, yes, for us to process our workflows, but I'm going to be concentrated on the pilot way, let's say, in this talk. Okay, so how do we do this using Glidein WMS pilots? Well, each pilot should now include also an additional slot, which will be the GPU slot, which can be run inside the pilot together with the CPU partitionable slot, which is what we have today. In principle, this GPU slot can be filled, the information for this GPU can be filled with a native tool, this Condor GPU discovery, okay? So we could use that. However, and this is a point we are discussing recently in WM and submission infrastructure, is how do we want to do this? How do we want to orchestrate all the possibilities in the sense of discovering the GPUs which are available? Because we have identified that we might be thinking independently of implementing this auto discovery at several layers in the stack. So at the software level, at the workload management level, and also in the submission infrastructure layer. So is this going to be leading to having redundant or even conflicting information? So do we want to really do auto discovery? And so we need to coordinate if we want auto discovery, which layer of the stack runs this. Also, auto discovery might not even be a good idea if we try to access resources which are in principle shared by multiple VOs, for example. I don't know, this may lead to, let's say, well competition for the resources and suboptimal optimization. Instead, what we think is that the way forward is to negotiate the requests, negotiate the resources with the local system, right? So, for example, by means of a Condor CE and batch system, so that the pilots present a request, and then these requests are granted by the local system and are redirected to the node proper, where these resources can be found. So once this is allocated, we need to tag the GPU resources, for example, the total GPUs, the CUDA capability, etc. So all this information concerning the type of GPU which is available to the pilot and to the slot. So some points about libraries. So GPUs, well, all payloads in CMS are executed inside the Singularity containers. Now, if we consider GPU jobs, then we need to have software libraries be available in the slot runtime. So, for example, already we have some specialized software like Singularity container for TensorFlow jobs, which are available via CMBL file system. In particular, OSG is supporting these libraries and being distributed via CMBL file system. So, images for TensorFlow jobs, for example. Additionally, one option that we have and that we are starting to use is to include the -NV tag when launching the Singularity, because this will also make available the host system libraries into the container. So these libraries would be available for the job. Okay. So the matchmaking. So now we have, let's say, in this stage, we have preloaded the slot with all the information. We have also the jobs with all the information on what GPUs they are requesting, the type, the need or not of GPUs. Now proceeding on to the matchmaking in Condor. Well, basically the main idea here is that we rely on the Condor features, of course. So matchmaking is produced via expressions in having to do with the attributes in the class sets, both of the machine and on the jobs, just like any other job. So yeah, GPUs have to be requested, the type of CUDA, etc. One thing is that we can run and load, let's say, custom-made Singularity containers, and this can be included in type of pilot. One point that we have been also discussing recently is what to do when we have multiply community of users and resources. So up to now, basically, you can auto-discover a GPU and you can decide to use the GPU. Fine, but what happens when we have the situation? So we would need to do accounting, sharing, imposing quotas, priorities, etc. Just like what we do in the pool for CPU jobs, of course. So the point here is to run a specific slot weight, which weights the GPUs that we find. And based on that, we can set accounting groups and add, yes, thank you. I'm finishing. So accounting groups, and from which we can distribute quotas and shares between users and also priorities. Okay. So just to say that we have some GPUs available in CMS. This is in particular in some of the US CMS sites, and they are being used. We have a particular way on which we can use these GPUs, which is CMS Connect, which is a lightweight WM service. This is independent of WMagents and CRUD, so it's not available for full cloud analysis or production jobs, but it's already available for users which can run on the pool. Okay. Finally, a note only on another topic, which is multi-node slots on the PCs. So we don't have a real need for this, of course, but it may be required due to the HPC scheduling policies, for example. In this case, we can use it because we can just launch a pilot, which spans several nodes, and we can run a StarD in each of the nodes, which will then, from that point on, operate independently. Okay. So I will perhaps just leave my conclusions to be read. That's all. Thank you.